Note 2, properties of limits, inspired by Grajeda. She put, let them have no limits. And I think she meant it like a play on words, but I thought it was cute and funny, so I put no limits in here. So when you see Grajeda, like, hey, Grajeda, you inspired Chavez for a hashtag. And yeah. Or you can show her this. Guys, these are properties. Don't freak out. They're very basic. Now we're working with two functions. So you know how yesterday we were just doing like limit with one function and one graph? So now they're just saying, well, what if I have two limits and can I do something with those? And yeah, you can. Oh, hold on, guys. Time out. All right. Sorry about that, guys. Here we go. You guys ready? So all this is, don't freak out. All they're telling you is that this limit has, that this function, as x approaches c for f of x, has a limit of L. And then they're telling you have another function in another graph somewhere, they're calling it g of x, and as x approaches that same x value, that has a limit of m. And because I'm approaching the same x value, there's some properties that I share. If I add them, f of x and g of x, you can add the limits. If I subtract them, usually they put these two in the same line and just put plus minus, but this textbook, the Demana textbook, wrote it in separate lines. If you approach L and M and you subtract the f of x minus g of x, you subtract. See, they're pretty basic. You can see, if you multiply, you can multiply. See, so if you multiply by a constant, you can multiply by a constant. If you're dividing, limit as x approaches c, as long as they're approaching the same value, the same x value, both limits, f of x over g of x, you can just do L divided by m. As long as m is not 0, because you can't divide by a 0. And same thing with the power rule. They're pretty basic. They're not extreme. It's kind of, I don't want to say it's common sense, but it makes sense. Like, okay, one limit is this, the other limit is that. I'm approaching the same x value. Yeah, you can just add up the limits. Does that make sense to you guys? All right, so here we go. We're just going to practice. I have two limits. Notice example 1, x approaches 4 for f of x approaches 4 for g of x. Is the x approaching the same, am I approaching the same x value on both functions? Perfect, so I can use my properties. Let's see what letter A says. Limit as x approaches 4 for g of x plus 3. Well, the limit for g of x was already 3, so what do you think this new limit's going to be? Yeah, there it is, that's it. See? And in case you're wondering, like, Chavez, I want a visual. I'm a visual learner. Okay, let me give you the easiest graph I can think of. I'm going to call this g of x. And if I want the limit to be 3 at x equals 4, the easiest line I can think of is a horizontal line that's always 3. Do you guys agree with that? Well, if I have this horizontal line that's always 3, and I do a vertical shift up 3, then my y value is always going to be, yeah, do you guys see how it works? Yeah, it works. Beautiful. All right, this one here. Limit as x approaches 4, so that means I can go 4 times f, let's see, what is the limit as x approaches 4 for f of x? 0? What's 4 times 0? Done. That's it. It's just, that's this limit right here. Constant multiple rule. Yes, miss. You see how it says x there? So that x is the number 4, because x is approaching 4. Yeah. Direct substitution. Sorry, that's not the constant. That's direct substitution. Maybe I should, next time I'll delete that one, because I think that one's too advanced. All right, this one here says g squared. So I take my g value, and I'm just going to what? Square it. What's 3 squared? 9. X is approaching 4, so let's see. G of x is 3 over f of x minus 1. So 0 minus 1. So what is that? Negative 3. Yeah, you're good. How do we feel, guys? Once you evaluate a limit, you don't have to write the word limit because we're evaluating it. You know what I mean? Okay. So let's go to the next one. This one is coming from UH, and it says, given limit as x approaches c of f of x is 3, x approaches c for g of x is 5, and x approaches c for h of x is 2. So I'm approaching the same x value for all 3. Do you guys see that? Find the limits that exist. If the limit does not exist, explain why. Okay. So let's see if we can figure this out. Does letter A, does that limit exist? What do you guys think? And it's okay to be wrong. I don't know, Chop. Yes, it does exist. I saw a thumbs up. Limit as x approaches c for f of x is 3 plus, this is a constant, so I'm going to go 5 times, what's the limit as x approaches c for g of x? 5. So let's see what this limit is. 5 times 5 is 25 plus 3. That's it? Yes. Oh, because I'm just using the properties. This can be broken down to limit as x approaches c of f of x plus, and you can put the 5 in the front, limit as x approaches c of g of x. And I already have this limit here. That limit is this one. So I put a 5 in there for that. And I already have this limit here. That limit is 3. See? So 3 plus 5 times 5. That makes sense? Yeah, don't worry. We'll get to some more that don't exist. And you'll see right now how. Maybe. Limit as x approaches c of g of x. Well, I already have that one. That one's 5. So all I got to do is write 5 and raise it to what power? To the third. I don't know. Was that 125? Okay. This one has a square root. I should have made it a negative 3. Darn it. Next time I'll try to trick you guys. Limit as x approaches 3, as x approaches c of the square root of f of x. Well, limit as x approaches c of f of x is 3, so this must be the square root of 3. Yeah. Correct. It would not exist. So the question that Abdul Karim asked is, and you're going to be asked this question on UH as well. What if the limit of x approaches c was a negative 3? Can you take a square root of a negative 3? No, not in the real number plane, no. So if it would have been negative, then this limit would not exist. Does that make sense? Yeah, you can't get a square root of a negative value. All right, here we go. This one here. I have a product, G and H, and then I'm dividing by F. Yes, you can take the limit of a product that is right here. See, it's row number 4. And then the row number 5, the quotient row when you're dividing. So yes, we can find that limit. So let's see, I'm going to go 5 times 2 divided by 3. Leave it as 10 over 3. So all of these you can solve. We'll get to one where don't worry, Gonzalez, we'll get to one where you can't find the limit. And you'll see why what's up in a little bit. How do we feel so far, guys? Okay, perfect. Example 3. It says, use the graph of the function f of x shown to the left in order to determine limit as x approaches 6 from the right. Yeah, that's not bad. Limit as x approaches 6 from the right. This is like what we did yesterday, right? Is equal to, as I approach 6 from the right, that looks like it is 3. Done. That's it. All right, let's go to the next page. And it says the function f is shown to the right. Determine the equations of all vertical and horizontal asymptotes of f and the equivalent limit equations. Okay, that's pretty easy. Where does it look like I have vertical asymptotes? For sure, it looks like a negative 1. And it looks like I have another one at 6. Now, horizontal asymptotes are end behavior. So do you see this graph flatlining somewhere? Yeah, I see 2 of them. Where and where? At negative 1 and at 4. Do you guys see all those dotted lines? Those are the equations I want. Vertical asymptotes. I'm going to write the word vertical asymptotes. And I'm just going to write x equals negative 1. And then I'm going to put the word and. X equals, is that 6? Yeah. Horizontal asymptotes. You can already see how they're related to limits, but we'll hit you again with these type of limits later on. Horizontal asymptotes, I have 2 of them. Y equals negative 1 and y equals 4. Oh, 4. It looks like 4. I make mistakes, but not right now. Sorry. No. I promise I didn't. No. We're good, guys. We're good. What's up, Miss? Ask. No, I make a lot of mistakes. Trust me. All right. Don't freak out. I have a composite function. I'm going to show you how to do it. I'm going to go slow. And then tomorrow or the day after, we're going to trick you. But don't worry, we're going to go slow right now. This one says, give the following graphs of f and g. So which one's f, which one's g? This one's f. I don't know if you can see it. This one's g. Find the limit as x approaches -1 of f of g of x in simplest form. All right, so here we go. I'm going to write limit as x approaches -1 of f of g of x. What you got to find first is the g of x. So I'm going to write limit as x approaches -1 of g of x. So go to g of x, go to -1, and it looks like that limit is, what does it look like? 0. Put 0. So now that is going to be my new x value that I approach for the graph of f. So I'm going to write limit as x approaches this value that you got, 0, of f of x. Do you see how we're doing it? So now I go to the graph of f. As I approach 0, it has to match from both sides. If I approach from the left, it is 7. If I approach from the right, it is 3. So this limit, yeah, and don't worry, I'll write better notes for you. I'm gonna split it up for you. Split limit as x approaches 0 from the left of f of x is equal to, and you guys told me that was 7. Limit as x approaches 0 from the right of the same function equals 3. So since they don't match, do not match. Since they don't match, we said that the limit does not exist. That is not a 1. That's a DNE. Does that make sense to you guys? Okay. I should have probably done one that does exist, but I apologize for giving you this one right off the bat. Next time. You know what? Let me put in here for the next year. Update notes. Update notes. Insert one that does exist. Okay, next year's notes will be better. Sorry, guys. All right, what's up? But not right now. Probably for like BC or something. All right, here we go. This one does exist. I should have put this one first. All right, so here we go. Which one is which graph first? This is the graph of G. If you can't see it, it's really light. This is the graph of F. I'm sorry, I don't know what it's called. Is it called OCD? Like where, man, Chavez, on the first one, on this one, you put the F on the left and the G on the right. And on this one, now you're putting the G on the left and the F on the right. Like, be consistent. Like, I don't know what it's called, if it's OCD or what, but sorry guys, when I type these out, I just type. I don't think of these things. All right, again, this is the same thing, so I'm gonna write up here where I have space. It says limit as x approaches 4 of f composite of g of x. So the first thing I'm gonna do is limit as x approaches 4 for the function g of x. So I go to g, it's in my left one. As I approach 4 for the function g of x, so y value is 0. So now I'm going to take that value, and that's what I'm going to approach. Limit as x approaches 0 for the function f of x. So here's my f. I'm going to approach 0 from the left and the right, and the y value seems to be 2. So that means this whole mumbo jumbo is just 2. What's up?
Okay, so for the limit of the first one.
Uh-huh.
So for that one, how would, like, if it was does not exist, the whole thing?
Oh yeah, if the limit of x approaches 4 of g of x, if it does not exist, then the whole thing does not exist. Because you can't find limit of f of, well, there is an exception, but we're not advanced yet. Here we go. We're going to use our properties now. So now it's not a big deal. I have the graph of f on the left. If you can't see it, I don't know if it comes out good because it's kind of like light. But the one on the left is f, the one on the right is g. We're just going to multiply. Limit as x approaches -1 of f of x times g of x. There's nothing more, so let's see what f of x is. If I approach -1, the limit is, what is it? -4 or -5? -5? Okay, sorry, I didn't hear you. All right, so -5 and then g of x. So I got to approach -1 for g of x. -1 for g of x, that looks like it is -4. I'm going to multiply those two. -5 times -4, that is negative. Oh, sorry. Not negative times a negative is a positive. There's my first mistake. I wrote a negative in there. Ask, what's up? All right, here we go. Oh, Chav, I can't do this one. Relax. Let's see. Given the following graph of fx, find the value of limit as x approaches. So this is f. Let's see. Maybe we'll have a conversation on this. Limit. So I'm going to write limit as x approaches negative 2 of f of x minus 3. All right. So just write this down for now. Here's how I see it. In a little bit, maybe it's easier. Maybe it's easier in a little bit. I see this graph that I'm looking at is f. Yes or no? I know that this part right here, f of x minus 3, this is a horizontal shift 3 to the right of f of x. Does that make sense? So if I see this graph here and I move 3 to the right, like where would I be? So let's see. You see how I'm going to go right to negative 2. At the moment, I'm at 2. Do you guys see that? So go 3 to the left on this graph, and that point, if you move 3 to the right, would be at negative 2. Does that make sense? All right, so I'm going to go 3 to the left. 1, 2, 3. So let's see. I'm looking at, look at that. I'm looking at negative 5. So that vertical asymptote, do you see how it's a vertical asymptote first and foremost? That vertical asymptote, if I move 3 to the right, would be negative 2. So what's my limit? I have a vertical asymptote. It is starts with a letter, and well, that's for functions. Does not exist. Do you guys see that? I think that's the easiest. I'll tell you another way. Relax. There's always someone that says, Chav, why can't I just plug in a negative 2 into the function? All right, fine. If I were to plug in a negative 2 in there, negative 2 minus 3 is negative 5, and then you look at negative 5, can I have a limit at a vertical asymptote? No. If you think that's easier, which maybe it is, go ahead and do it that route. But I want you to know that this is a horizontal shift 3 to the right. We're in the clear, Valencia? For sure? Okay. Do you guys just think it's easier just to plug it in? I mean, okay. I just want you guys to make sure that you know that f of x minus 3 is a shift 3 to the right. You guys good? Okay. You okay? All right. They're a little pink, a little bit. Did you yawn? Yeah. Oh, okay. I was about to say, like, get some sleep. No, this is not okay. Get some sleep, for real, please. What's up? There can't be a limit on the vertical asymptote. You can have a behavior like negative infinity, positive infinity, but you can't have a limit. What's up? Sorry about that. Yeah, like this whole graph, all of it, everything. Imagine that you shift all these curves 3 times to the right. Then that vertical asymptote at negative 5 would be a negative 2. You know what I mean? Does that make sense? Okay. All right, let's keep going. That one was kind of hard. I might, you know what? Let me put an asterisk and put update for next year. Yeah, I'll see. I'm updating. Sorry, guys. This whole notes is going to look fresh next year. Example 9. Use the graph of the function f of x shown below in order to determine all values of a, for which the limit as x approaches a equals negative 2 on the interval negative 9 to 9. If there are no values of a, state none or write the empty set. Oh. The easiest way, in my opinion, here's the easiest way in my opinion. Make life easy. I would write a horizontal line at negative 2. So here's my horizontal line at negative 2. You see that red horizontal line? That's negative 2. And then I would look at the x values for where this function, the curve, approaches that line. Does that make sense? So I know I can see that at negative 6, so limit as x approaches negative 6 of this function, I know that's negative 2. Do you see how I did that? And then I see another one. Where's another one? Negative 1, so limit as x approaches negative 1 of this function is negative 2 again, and I have 2 more. Where else? At 2, limit as x approaches 2 of this function is also negative 2, and then one more, 7. Limit as x approaches 7 of f of x equals negative 2. Of course, delta doesn't want you to write limit, 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 limit. It says find the a values, so you're probably just going to have to write a equals negative 6, comma, negative 1, comma, 2, comma, 7. And they're probably going to have boxes. What's up? Okay. Yes, S. What is the A? Oh, see how up here it says, let me zoom in. See how it says limit as x approaches A? So these are all the values for A that will make this statement true. You know what I mean? Yeah, good questions. Keep asking. Dime más. Yeah, of course. Yeah, draw this happy face. No, you don't have to draw that. Sorry. Don't get mad at me, miss. Are we good? Okay. What's up? Oh. All right, here we go. You good, Gonzalez? We kind of already touched on this. Continuity at a point. So continuity at a point. Let's see what it says. A function is continuous at an interior point C if its domain. Okay. All that means is, okay, here we go. Let's go ahead and draw something. You don't have to have a bold dot for it to be continuous. If you see a curve, it's continuous, right? But I'm trying to prove a point here. So in this case, you see this graph that I just drew? In this case, the limit as x approaches c of this function is equal to f of c, which just equals L. Because you're defined. You're continuous. You're defined at c. Does that make sense? Like f of c literally gives you that number L. But if I were to draw a graph like this, so this one's continuous. So now I'm drawing, I'm going to change my colors so we can make sure that it's not the same. So if I were to draw this, here's C, here's L. Now look at this one. Limit as x approaches C of this function is definitely L. That's the limit. But if I were to tell you what is f of C, you're not going to tell me L. You're going to tell me undefined. Does that make sense? Chavez, I don't see the connection. I don't know what you're trying to tell me. I have no idea what you're saying. I'm going to slow down. What I'm trying to say is this. For you to be continuous, you can't be undefined. Like the limit has to equal the same as your function at that value. So this is the true definition of continuity. If the limit equals the function at that value, equals the same. If the limit is the same value as the function evaluated at the next value, if those are the same values, you're continuous. I hope I'm not saying it weird. Does that make sense? It has the same y values. The limit of x approaches c is L. The function evaluated at c is also L. Ask, please. Yes. So let's put numbers. Instead of saying c and L, let's say this is 3 and that's 5. 3, 5. See how my limit of this function, I'm going to put 3 here and I'll put 5. The limit of that function is 5, right? But if I tell you, like yesterday's notes, tell me what f of 3 is. Well, f of 3 is also 5. See how they match? So it's continuous because that's the definition. My limit is the same as the function that's evaluated at that x coordinate. Cool? But look at this one here. I'm going to do the same thing. I'm going to call this 3 and I'm going to call this 5. This one has a limit as x approaches 3 of 5, but f of 3 is undefined. Or it could have been, it doesn't have to be undefined. Let's say f of 3 is up here. I'm going to call that 8. And f of 3 is 8. Does it match? No. If it doesn't match, it's not continuous. Correct. There is a technical word for this. This is called removable discontinuity. Maybe I'm getting ahead of myself. I think I am because then I am. I'm getting ahead of myself. All right. Don't worry. You don't have to write that down because we're going to write it down here. And I had to remind myself, so I put one of the special ones here. So there are 4 forms of discontinuity. Okay, before I even continue, do you guys know what I mean by continuous and discontinuous? You can be honest. No? Okay. Okay. I'm going to say it anyways, even if you know it. Continuous means I can draw a curve without lifting this pencil. All that is continuous. If you have a hole all of a sudden, like right there, that is not continuous, because in order for me to draw this curve, I'd have to go like this, and then when I get to that removable discontinuity, I have to lift my pencil up and then go put it back down and then continue. Does that make sense? So that is called discontinuity. All right, here we go. That's the non-technical. This is the one that is not very common. This is called, it has several names, but I think the most common name is oscillating discontinuity. At x equals 0, it is discontinuous. Why? Because it is bouncing so fast. As you get closer and closer to 0, it's going boom, 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 boom. Sorry, I didn't have to. Like, imagine you're at a workout class and do the oscillate. Like, that means go jump up and down, jump up and down, jump up and down. Do you know what I mean? So, like, it looks like this. Watch. And I know this, it's already there, but it probably looks something like this. It's curve, curve, more. And then you're jumping so fast that you can't, like, look how fast it's jumping as you get close. This is not actually how it looks. There's a whole bunch of garbage in there. But it's jumping so fast that you can't tell if it's continuous or not at 0. So that's called oscillating discontinuity. Cool? I'm sure there's models where, you know, I'd have to think about like situations. Yeah, so that's the one that's not so common. I don't think they'll ask you that because there's not really anything exciting about that. But here are the 3 that they can ask you. You guys ready? You already know this one. Perfect. That's a hole. The technical name. Did you guys remember the technical name? Perfect. Someone said it. What is the technical name? Perfect. Removable discontinuity. I just put DISC. Don't read it as disc. It's discontinuity. Removable discontinuity. It's a hole. Removable discontinuities are the only ones that you can make continuous if you fill in the pixel. Don't worry, we'll get to that when we get to it. Here's the other type of discontinuity. I'll change the colors for you. If I have this, so I have something like this, and then I have something like that. What do you think that's called? Take a guess. It's a piecewise function. There's a gap in between. What do you think that gap is called? It starts with the letter J. And it's okay if you don't know. Second letter U. A jump. It's a jump discontinuity. It's a jump discontinuity. Good job, miss. And here's the third. What am I drawing here on this one? It's a vertical asymptote. This is called, the technical term is called infinite, and it has another name, but this is the one that's called the most. Infinite discontinuity. And it's also called, let's see, I'm trying to think. Oh man, I just had another infinite discontinuity. I know I'm going to see the word somewhere, and I'm going to be like, oh, that's what it's called. I can't remember right now, guys. Infinite discontinuity. Relax. It's real easy to understand why it's called infinite discontinuity. Does it go up forever? Do you ever cross it? That's why it's called infinite discontinuity. The discontinuity goes on forever. You can never cross a vertical asymptote. Cool? You cannot make infinite discontinuities and jump discontinuities. You can't make the blue graph and the green graph. You can never make them continuous. The only graph you can make continuous is the one that has a hole on it, if you fill in the pixel. That's the only one. We'll get to the situation where we'll ask you, make this continuous, and you'll figure it out. We'll do it. Cool? Okay. Let's continue, guys. I think we've covered... All discontinuities can be classified as removable and non-removable. Okay. This is a removable discontinuity, the one in red. The blue and the green is non-removable because there's nothing you can do to make them continuous. Does that make sense? Okay. So I hope I wrote that in there. Let me see. Removable discontinuities occur when the function has a limit, holding the graphs. Non-removable discontinuities occur when the limit of the function does not exist. Jumps and vertical asymptotes. Yes, I covered that right there. So make sure to put a star on that. You're gonna probably have questions on that. Here's the same graph we worked on yesterday. When I design these notes, it's by design. I don't want you guys to freak out. I'm freaking out. Sorry. I apologize. It's the same graph from yesterday, so no one should be freaking out. You're gonna tell me what type of discontinuity I have. Cool? First, let's answer the first question. Find where the graph is discontinuous. Technically, at your endpoints, you're continuous because it's part of your domain and it's a solid, so don't worry about the endpoints. Where am I discontinuous? At, on the right. Yeah, perfect. Discontinuous at x equals 1. Where else? Okay, and is there any other point? That's it, right? And now I have to identify the type of discontinuity. At x equals 1, what type of discontinuity is that? It's a jump. X equals 1 is a jump discontinuity. And then what about at x equals 2? Yeah, give me the technical. Perfect. A removable discontinuity. If you want to put at x equals 1, you can also put in quotes. It's a non-removable discontinuity. Are we okay? Oh.
Mr. Chavez?
Yes, ma'am.
Can you please post your attendance and put down your roster?
Yes, ma'am. Okay, 30-second break. So guys, it has been done. You guys ready? All right, we're just identifying discontinuities. So it's going to be fun. Find where the graph is discontinuous, identify the type of discontinuity. So I'm discontinuous, let's go left to right. Discontinuous at x equals -4, where else? X equals 1, where else? X equals 6. At those 3 x values. They want me to say what type? So let's see, at x equals -4, that is a removable. You could also say, oh, that's fine. That's the at x equals 1, that is a jump. You could also say non-removable, but jump is the preferred term. And then at x equals 6, that is a removable. Yes. Why a what? At -4. I have a hole. You cannot draw that graph without lifting the pencil up because there's a pixel missing. Oh, you said at 1? I have a jump. I have a jump. There's no way to draw that graph either without lifting the pencil up. You know what I mean? Okay, sorry, I thought I heard -4. All right, here we go. We're just identifying discontinuities. Find where the graph is discontinuous. All right. Find where the graph is discontinuous. All right, here we go. Left to right. We have a discontinuity at -6. We have another one at -3. We have another one at 4. And it looks like that's it, right? All right. At -6, what type is it? Removable. At -3, what type is it? Infinite. And at 4 is an infinite as well. Does that make sense, guys? Okay.
Yes,